Welcome to lab number 5 of CE371. This short video will provide an overview of the laboratory procedures. I encourage you to follow along on the written procedures provided in your lab manual. During this video, additional detail will be provided beyond the content in your laboratory manual. Remember, there will be a quiz regarding these procedures at the start of the lab period. Lab number 5 is the unconfined compression test. The lab procedure outlined here will allow for determination of the unconfined compression strength of a cohesive soil. With multiple iterations of this test, relationships can be built between the moisture content and the unconfined shear strength of the soil. In addition, the stiffness of the soil can be determined through this test. During this lab, be careful to load the soil at a constant rate. Avoid the desire to load the soil quickly in order to expedite the test and get out of the lab early. The first step is to utilize the 3 soil samples provided to you. At your workstation, you should have a plastic bag, and inside one bag you may find 2 or 3 samples already prepared at particular moisture contents. We want to remove one of those bags and place it off to the side. Don't open up the bag until we're ready for the sample. To conduct this test, you utilize what's known as a Harvard miniature mold. The miniature mold should be already assembled and at your workstation. We're going to spray down the mold using a releasing agent. As we did with the compaction test, we want to place the mold off to the side, and you do want to spray the mold liberally. We don't want the releasing agent running down the side per se or dripping down the side. We do want to make sure the entire interior is fully coated. Now we're ready to compact the sample inside the Harvard miniature mold. We're going to open the bag, and we're going to utilize a teaspoon or just our hands to place soil down into the miniature mold. What we're going to use to compact the soil into the mold is the Harvard miniature hammer. Now, this hammer is actually spring activated. We're not necessarily worried about the weight of the hammer or the height of the drop of the hammer. Instead, what we're doing is just simply breaking the spring in the manner I'm showing here by pushing downwards on the upper portion. When we've broken the spring, we've actually applied enough force to go past the resistance of the spring to release it, and we've applied enough energy downward onto the soil. Ultimately, we're going to compact a total of 3 different layers. Each layer gets a total of 25 blows from the hammer. And our third and final lift, after it's been compacted, should be above the interface between the lower portion of the mold and the collar of the mold. This is just like the compaction test where you performed a process of compacting soil in the larger compaction mold. And in that case, we required that that third and final lift of soil was compacted to a level that was above the interface between the mold and the collar itself. We want to make sure we do the same thing in this process. So I've got enough soil inside the Harvard miniature mold. I'm going to go ahead and compact the first layer. After each time of pushing down on the hammer, we'll make sure you're moving the hammer around on the surface, so we're completely compacting the entire surface. And assume I've reached 25. Again, just like in the compaction lab, we want to utilize the tool to go ahead and scarify, to scratch up the individual surface, so that again we don't end up with just 3 different layers compacted on top of each other. We want one homogeneous soil sample with an even amount of compaction and no obvious break between the individual layers. So now we place in enough soil to get our second layer. And again, 25 more drops of the hammer. Assume I've gotten the 25 there. Scratch up the surface one more time. And add in enough soil for your third and final lift. Again, keep in mind, after it's compacted, we want that final surface of the soil sample to be above the interface between the bottom of the mold and the collar. So make sure we're adding enough here for that final layer. 25 more blows with the hammer. Again, continuing to move the hammer around on the surface. And then assume I've reached my 25 drops of that hammer. We now want to go ahead and remove the sample and trim down the sample. So to remove and to start that process, what we do, remove the wing nuts from the top of the hardware miniature mold apparatus, and this top plate should slide right off. Place that off to the side, and at this point we should be able to remove the bottom plate, and now our sample should be compacted inside of this object. Okay? Now, the bottom and the top have collars. The bottom collar will likely just slide right off. You might give it a slight twist. We can see a portion of our sample has extruded out the bottom. That's perfectly fine. The top we don't necessarily want to break off. So to remove the top, what we want to do is place it inside this apparatus. When you place it in here, you hopefully can see on the video that there's a handle here on the back side. We want to make sure we're elevating that handle so that the teeth on the handle are now located just below the top of the collar. With the miniature mold pushed into this apparatus, we can now actually lift up, and it pulls the collar off the soil sample straight up. And in doing so, what we've provided is a scenario wherein I've got soil still pushed out up above this sample. So now we're ready to trim down the sample. To trim it, we've got a variety of tools to utilize. We've got actually a wire cutter. There's a couple other tools, but I recommend utilizing the wire cutter. Simply lay your sample down, or your mold rather, the hardware miniature mold, down on the table. And nice and slowly and evenly use that wire cutter, wire saw, to trim the sample. Go ahead and rotate the mold several times to make sure we're trimming this sample down right even with the top of the hardware miniature mold. We're going to do the same thing now with the base. Again, make sure you rotate that mold a few times. Drag the wire so it's stretching right across the mold, and make sure your soil sample has been trimmed down all the way. Now we want to go through the process of actually extruding the sample from the mold. We're not going to simply push this out with our fingers. Again, we're going to go back to this apparatus. You'll notice that the bottom of the mold has a series of grooves in the base, or at the bottom portion. Again, just like we did previously, we want to slide this in, and when we slide it in, there's a portion of this that will slide right into those grooves on the base. Now this part of the process is a two-person job. What we want to do is we want to make sure that we catch the sample. We don't want to allow the sample to push out and drop to the ground because that would damage the sample. But we also want to make sure we're not hurting anybody's hands or fingers. So look closely at this process. We've got a spatula here. you want to take the spatula and you want to reach inside the handle. Don't reach underneath the handle, because when your partner pushes down on the handle, that's going to end up coming right down on your hands or your fingers. You want to reach through the handle with the spatula to catch the sample. One individual is going to be pushing down on this lever, while another, or the same individual, can be pushing down on the top to make sure the entire apparatus doesn't flip over. And then in one nice smooth operation, we've caught the sample as it extruded out of the mold itself on the spatula, and now we can simply pick it up and move it over to the side for subsequent testing. Again, in this process, make sure that you're reaching through the center of the handle in a manner that avoids your hand or your fingers getting pinched by this handle coming down too far. And then don't simply push down on this, because the entire apparatus does have a tendency to get top heavy. Make sure somebody else is pushing downward here at the same time we're pushing down on this portion. We're now done with the extruding tool. At this point, we want to quickly, because we're losing moisture from the sample, we want to quickly weigh the sample. We can weigh this on our smaller scale. Make sure you record that weight for that particular sample. And then we're also going to use our digital calipers to measure the dimensions, to measure diameter, and we also want to measure the overall length. Make sure you're using the right portion of the calipers to measure those dimensions. Likewise, make sure you're taking at least 3 readings of all these dimensions, and then take an average of those 3 readings to be a representative value for the sample. Next step in the process is to start to load up and take our sample to failure. We'll use our single axial compressive machine. The intent is to place your sample inside the machine. However, it's critical we place these small white filter papers on both ends of the sample before we place it into the machine. There's a critical reason for those filter papers, which is typically a question as part of your lab write-up. So make sure you've got filter paper again at both ends of the sample. Simply slide it in the machine. If there's not enough room, you can back off this machine. If you go counterclockwise, you're going to open that up and provide enough room to slide your sample in there. Now we want to go ahead and make sure that there's a seating load on the sample, but we also want to zero out our gauges. To apply load, that is to close up the gap and start to apply load to the sample, we turn this handle in a clockwise direction. What we're going to do is we're going to continue to turn this until on the dial gauge associated with the proving ring, we start to see some movement. As soon as we see any value, any movement in that needle, we want to stop applying the load. And just there, I started to see actually some movement in that needle. So at this point, we've applied a seating load. That is, the sample is just barely under any compressive strength, or under any compressive load. At this point, we want to zero out the gauges. There are 2 dial gauges we're going to utilize in the lab. Again, the first dial gauge is associated with the proving ring. And to zero that out, it's simply as easy as don't try to move the needle itself, but we're going to move the numbers. So if you need to, you can loosen up the small knurled nut here on the outside, which allows you to very easily turn the readings on the gauge, and make sure 0 is lined up with your needle, and then tighten that back down. Now we want to do the same thing with this. This gauge is actually going to read displacement, or how far did the sample deform. So it's measuring change in length, whereas this one is actually going to give us a measurement of load. This one, we want to make sure that it has a minimum of 3/4 of an inch of travel associated with the plunger on the dial gauge. So on this setup, we've got a pretty well set up dial gauge based on where it's located. I've got at least 3/4 of an inch of distance of travel. for the dial gauge in the plunger. If needed, we can adjust that location by moving this platform either up or down as needed to make sure you've got enough distance of travel. Once we've confirmed that, again, we can go ahead and zero this one out. Same process, loosen this nut on the top. Turn the numbers so that 0 aligns well with your needle. Double check that everything's at 0 before we start the process. Now what we want to do is we want to deform the sample by adding load, and then we're going to take readings at particular movements in deformation. We're going to take readings of load at given values of deformation. If you take a look at the data sheet associated with this particular lab, you'll see that along the left-hand side you've got displacements or deformations in inches. So we need to read the dial gauge, and when we meet one of these numbers, one of the lab partners should be calling out to take a reading. The other lab partner should be recording or reading and recording the number on the dial gauge associated with the proving ring. That is the load that the sample is undergoing at that particular displacement. At this point, it's critical that we load the sample at a constant rate. The rate we're looking for is to turn the handle one revolution, that is one time around every 3 seconds. That is a painstakingly slow process, particularly if you're looking to get out of the lab quickly. Do not rush this part of the process. If you load your sample too quickly, you'll get some false data and the quality of your report is going to significantly decline. So turn the handle. You're going to turn the handle in a clockwise direction to load up the sample at a rate of roughly one revolution every 3 seconds. Again, making sure that somebody is calling out when to take a reading on the dial gauge based on the readings that are shown on the dial gauge here for deformation. When your sample has reached failure, we want to actually make sure we take a sketch of that. We can confirm that we're at failure if the sample has deformed upwards of 0.675 inches. In fact, eventually you'll run out of space on your data sheet. If we've completely filled this up, the assumption is that we've displaced the sample. We've gone through enough strain to consider that the sample has failed. So enough change in length relative to its original length that it has strained sufficiently to be considered at failure. So if you complete your data sheet, you reach 0.675 inches of deformation, go ahead and terminate the test. The other way we can confirm that we've reached failure is if we see some sort of failure surface developing in the soil sample itself. Typically that failure surface will have a classic plane. Again, that is a question associated with your lab write-up, and you should be looking for a particular surface or surface plane of failure in the sample. Make sure you take the time to do an accurate sketch of what that failure surface looks like. So we want to go through this process now, again loading this up, one revolution every 3 seconds. As I'm loading, I'm watching the change in this dial gauge indicating displacement. When my partner tells me we're at one of those values, we don't want to stop the loading process. It's a continuous loading process. So when we reach that value, somebody needs to call that out. Another individual needs to record the load, shown up here on the proving ring, and continue that process without stopping, but at that slow rate of one revolution every 3 seconds. Okay? Now, assuming I've taken that sample to complete failure, the next step after we've drawn a picture of the sample is to recover a moisture content associated with that particular sample. As I indicated, you start out with 3 different bags of soil, 3 different moisture contents. Those moisture contents are not provided to you, but we determine those as part of the lab process. Assuming that I've got a sample here, and I've got another sample already prepared, assuming this one has failed, we want to go ahead and we would make sure that we break open the sample. Just like we've seen before, we're going to recover the moisture content sample from the center of the soil. To do that, while it's not explicitly called out in your lab procedures, because we've done moisture content tests multiple times at this point in the semester, do make sure that you match up the lid of the tear can with the base of the tear can. Make sure you're recording the weight empty of both the tear can plus its lid. Record that empty weight, and then recover some moisture content sample from your tested and failed soil sample. As we've seen before, 2 to 3 teaspoons of that soil would be sufficient to get an accurate moisture content reading. Once we've got soil inside the tear can, get a new weight of the soil plus tear can plus lid, record that information, place the lid canted to the side with an opening to allow moisture to escape at this point. Place the can in the location directed by either your lab instructor or the lab technician. Those will be placed in the oven overnight, and the numbers will be emailed to you the following day. After we've taken that moisture sample away, we can go ahead and place the remaining soil back into one of the available bags, and then we're going to repeat this process. There's a total of three of these tests associated with creating enough data to conduct your lab experiment. So we're going to repeat the original steps 2 more times. Again, 1 time for each sample that's located in each of the 3 bags. And again, each of those samples is at a different moisture content. Ultimately then, you're going to plot the normal stress, plot normal stress versus normal strain to determine the elastic properties of the soil. Remember, however, you're measuring deformation and load. That information needs to be converted from deformation and load into stress and strain. You're also asked to plot the stresses at failure as a Mohr circle to determine the cohesive strength of the soil. That completes Lab 5. Before departing the lab, ensure that your data sheets are completely filled in. Wash the desk at your workstation. Make sure you sweep up the floor around your workstation, and then check in with your lab instructor one final time before departing the lab. That completes the Unconfined Compression Lab test for CE371.